So I'm Bill Van Bsien. I'm in the embedded flight software group at the Johns Hopkins Applied Physics Lab over in Maryland, where we host this workshop every other year, or at least try to. This summer and into the fall, we completed a trade study in how to maximize data return from the Europa lander and possibly just extend its lifetime on the surface. I think already, there we go. We did talk a little bit about the motivations for going to Europa, which basically boils down to the fact that at this point it's probably the most likely candidate for finding life elsewhere in the solar system. It has all the three necessary requirements. It's got water in the subsurface ocean. It's got an energy source that comes from tidal heating of Europa as it's continuously deformed as it completes its revolution around Jupiter. And it has chemistry and potentially organic molecules, and all three of these together can be amenable to having life. And the reason for wanting to have a lander as opposed to just a flyby is that when you're on the surface, you can do some more interesting science. You can break rocks apart, characterize surface samples, things like that. Also understand the seismic activity, which can give clues as to the internal structure of Europa. What the mission's going to look like, it's going to be a pair of spacecraft that's going to be brought into orbit and then to Europa on a single launch vehicle, an orbiter and a lander. Once at Europa, the lander is going to separate and descend onto the surface. And its landing spot on the surface will have been reconnoitered by the Europa Clipper, which will have launched a few years before. This mission is still much earlier in its development cycle than the Europa Clipper is, so it will probably launch about 4 or 5 years after. So once the lander is on the surface of Europa, the orbiter will be the primary data relay back to Earth. However, there will also be a secondary data relay back to Earth via the Clipper. But this link won't be optimal. It's really just an emergency link. From the point of view of the lander, the Clipper is going to have a very erratic orbit. So that link is going to be characterized by high latency and intermittent connectivity and probably low data rates. So as to the challenges of communicating with the lander on the surface, Jupiter is famous for having the extremely harsh radiation environment that can interfere with communications and damage electronics. We also have to contend with this interesting scenario of having multiple Earthbound links, sometimes with very high latency and periodic communication windows. And I think what's most interesting and relevant to this talk is that the lander is going to have a battery that is not rechargeable, just a fixed energy budget. And all the instruments, all of the major spacecraft subsystems have to share power from this. And so we want to see what we can do from the telecommunications point of view to reduce that burden on this very finite and precious energy budget. So the motivating question for our trade study was, given these networking challenges and given this finite energy budget, can we extend the lifetime of the lander on the surface, or at least maximize the overall data return by intelligently applying CCSDS DTN protocols and tuning properties of the RF system and seeing if they can be co-optimized together. So we had a pretty broad mandate for the trade study. Basically, it was just investigate what happens when you apply CCSDS protocols to the networking stack and understand the implications of that. And because of this broad mandate, we iterated several times over it. And with each round of the trade study, we tried to get more precise data and more valuable data. In the first round, we just wanted to develop an intuition about how network and application layer protocols affect link efficiency. So basically, we wanted to measure what is the cost of adding extra protocols into the stack. So how much do their headers and trailers affect link efficiency? What's the ideal packet size? And then what's the cost of retransmissions for these various packet sizes? In the second round, we went a little bit deeper. We tried to look into the link layer. The plan is for the Europa lander to use the PROX1 protocol, which is a CCSDS-defined link layer. And in it, we refined the initial results. We modeled CFDP protocol exchanges, encapsulated link layer frames, and one of the things we really wanted to identify is what the ideal frame size is going to be. And then in the third round is, I think, where the trade study really came together. So we combined the results of the first two rounds with properties of the RF system. So we parameterized our simulation scripts and models to take into account transmission power, bit error rates, things of that nature. And I think the results are really surprising there. So before I get into the first round too much, I'll talk just briefly about the CCSDS protocols we considered in the top right. CFDP, I think, should be familiar to a lot of people here. That's the CCSDS file delivery protocol, and it provides FTP-like transfer across, intended for space links. It does have some degree of retransmission, so it can provide reliability, but it's not really optimized to do so. BP is, I think, one of the most sophisticated protocols in the CCSDS DTN networking stack. It provides a lot of high-level features like reactive fragmentation, route scheduling, custody transfer across these space links. LTP, I think the intention is to be the TCP-like equivalent to provide transmission control and reliability. So the three stacks that we considered in the first phase was a networking stack of CFDP on top of BP on top of LTP. We considered CFDP on top of LTP, cutting BP out of the loop. And then we also, as a baseline, just wanted to measure CFDP directly over the link layer, although for this phase we didn't measure the link layer. So our first main objective was to understand the effective packet size on link efficiency under various bit error rates. So we wanted to measure the overhead that would be introduced by CFDP, BP, LTP, understand how should I phrase it, the cost of retransmissions. So if you have a small packet, there's fewer bits that need to be retransmitted, but then the problem is if you have smaller packets, you have more packets, and there's a fixed overhead for each packet, so that itself can affect the efficiency. Another objective was a little bit more intangible, and we wanted to identify what the stakeholders were in the system and what their interests might be. So for example, CNDH mission ops, the telecommunications team, sometimes they have competing interests, and what's good for one might carry something that's too burdensome for the other in terms of either design constraints or power constraints or something like that. And our methodology for this first phase was that we leveraged a series of really nice spreadsheets that were designed as part of an earlier NASA-funded R&D effort that would do this kind of estimating and measurement of packet overheads and link efficiency. And I guess I should note that we define efficiency here as the ratio of bits in a data file. So let's say you have a science data file of 10 megabits, but in order to successfully transmit it to the next node along the way, let's say it takes 20 megabits to account for retransmissions and packet headers and things like that. Let's say it's 20 megabits, then the efficiency would be 50%. These are the results from the first phase. The first major finding is that both BP and LTP add negligible overhead, and it's barely perceptible. And so for the rest of the trade study, we kind of discounted BP and LTP just to simplify things because of this finding that they really they don't incur any cost in terms of link efficiency. LTP, very unsurprisingly, helps to maintain high efficiency in lossy settings, which means bit error rates of 1 in 10 to the third, so about 1 in 1,000 being dropped. And this isn't surprising because that's what LTP is supposed to do. And then we also found that CFDP directly over the link layer, so not being carried by LTP, can achieve good efficiency on lossy links, but at a cost. And that cost is in this chart. And so this is a measurement of the number of operations that need to be done to process a CFDP transaction as a function of CFDP packet size. So this is a log scale, so it's not too easy to read. But around here, this is a CFDP packet size of about 1 kilobyte, whereas out here, this is a CFDP packet size of about 64,000 bytes. And so in order to maintain good efficiency on the link by having really small packets to optimize for retransmissions, there's a lot more packets that need to be processed, and there's a fixed cost per packet, and so that's what's measured here. You're increasing the burden on the CNDH processor by a pretty dramatic amount versus having a larger CFDP packet size. So this graph on the top left compares CFDP efficiency versus a full DTN stack efficiency as a function, again, of CFDP packet size. So the light blue is the DTN stack. The dark blue is just CFDP if it's right over the link layer. And then this graph on the bottom right just shows a degradation of efficiency as CFDP packet size increases. So in the light blue case here is a very high error rate scenario of 1 in 10 to the 4th, where I guess that's 1 in every 10,000 bits would be an error. So as a CFDP size goes up, we're actually only getting 20% efficiency because so much of the link is wasted for retransmissions. So in the second round, we went a little bit deeper. We wanted to look at link layer effects, and among other things, we wanted to identify what the ideal link layer frame size would be. And so I guess before I get into that, I'll talk about Prox1 just a little bit. It's one of the more recent CCS-defined link layer protocols. It's important because it's the highest layer at which the radio has awareness, and it's used to do all sorts of important things: negotiate bit rates, populate sync patterns, detect and correct errors, things like that. It does contain extensions for retransmissions, but for the purposes of this trade study, we didn't use it. We assumed all reliability would be handled at higher layers of the networking stack. Our approach here was we modeled CFDP endpoints using a series of Python scripts. So they would simulate CFDP endpoints and perform a simulated file exchange over that. And then what we did was we wrote some extensions for it to encapsulate the CFDP packets into frames. And so we kind of parameterized these scripts with 3 things. So there were 3 degrees of freedom. There was frame error rate, which we varied from 1 in 10 squared. So 1 in 100 frames being dropped to about 1 in, 100,000 frames being dropped. We varied Prox1 and CFDP packet sizes. So we varied the Prox1 frame size from about 128 bytes to its maximum of 2,048 bytes. And then we varied the CFDP packet sizes from about 1 kilobyte to about 64,000 bytes. And again, we assume no link level retransmission. We assume that would all be at the CFDP layer. So these are the results we got. The most glaring finding is that in every case, in every error rate condition, having the maximum link layer frame size was optimal. So these graphs are our results. On the vertical axis is efficiency that goes to a maximum of 1.0 or 100%. As you move to the right, that's increasing CFDP size from 1K to, I can't read that, it's probably 16K. And then as you go back, on the axis going backwards, that's increasing frame size. And so there's a little annotation right there for what is the maximum on each of these curves. This this graph on the left is for a frame error rate of, I guess that's 1 in 10 to the 3rd. I can't do 0.01% to exponents in my head. But it's a pretty good error rate. This is a much higher error rate, meaning much more frames are being dropped. So what's interesting here is that CFDP size is still the driving factor in efficiency. So when we have pretty good error rates, meaning there's not many, the ideal CFDP packet size is quite large, close to the maximum again, if this is probably about 16K. Here, when we have tons of frames being dropped, the ideal CFDP size is much smaller, closest to the minimum. And I think that's about either 1K or 2K right there. And now for the third phase, was really exciting for me, and I think exciting for all of us, and where it really all came together. Before we get into it, it's important to kind of understand the basics of this graph, and we definitely spent hours poring over it, and it contains such a load of information, and it's kind of overwhelming at first, at least it was for me. But for right now, for the purposes of understanding the third phase of our study, we can limit ourselves to understanding what this one curve means. So it's that solid blue line that is pointed to by the solid blue curve that's pointed to by the orange line with the label of 1024. And what this graph does is it relates EBNO, which is energy per bit, or basically a proxy for transmission power, to bit error rate. So as you move down on the vertical axis, this means you have fewer bit errors. And then as you move to the right on the horizontal axis, you're increasing the power. So the intuition here is that as you increase the power and you move down along this curve, your bit error rate improves, meaning you have fewer bit errors. But there's a catch, and there's a few other things at play here. So first of all, this is a log-log scale, so this axis is logarithmic, so is this one. For every 3 dB step along here, you double the power, but you half the bit rate. So as you move down and to the right on the curve, you're increasing the power, but your transmission speed slows down. So one of the effects that we wanted to study was that as you move to the right and down on that curve, you're having fewer bit error rates, which means there's fewer packets being dropped and fewer retransmissions, but your bit rate is also slowing down. So we want to identify, really, is there any sweet spots along this curve which balances the best of bit rate and having a good signal. So we asked a few main questions. For a fixed energy budget, how can we maximize the amount of science data retrieved off the lander, so optimizing for time to downlink a file. And then we also wanted to try to optimize for energy efficiency. So given a file of fixed size, how can we downlink it with the least amount of energy possible? And again, we want to identify, would these be the same setting on the EBNO curve, or would they be different points, and is there some balance between the two of them? So the way we did this, we took our scripts from the second phase that modeled the link layer, and we parameterized it even further with the physical layer properties. So we took a few candidate points along this EBNO curve. I think we picked like 5 or 6. So 5 or 6 different transmission powers, and then ran our script again with each of these 5 points, and then over various frame sizes and CFDP packet sizes, just to see what would be most efficient, the most efficient use of the link, what would be most power efficient, and what would be fastest. So I think one of the most surprising results for me was the finding that the cost of retransmissions can be cheaper than the cost of maintaining a perfect channel. So what that means in terms of energy efficiency. So it's a little counterintuitive, because you'd think, well, you're dropping so many frames, you're dropping so many packets, you have to retransmit, and because you're doing all this retransmission, you're going to use a lot more power because you're going to spend more time transmitting them all. But the finding is that it's actually worth it to drop all those packets, drop all those frames, and retransmit it. It's still more energy efficient than using a high transmission power and having no retransmissions. And so the graph here, the blue line represents the amount the amount of energy consumed as a function of transmission power. And these were, it's the same axis as in that Ebno curve in the previous 2 slides ago. So what we see as transmission power increases, the amount of energy expended to downlink that file also increases. But what's not really shown here is that here we're dropping and retransmitting so many packets, but it's still worth it. The catch, though, is that the time it takes to downlink a file improves as you increase transmission power, which is also a little bit counterintuitive because as you increase the power, the bit rate goes down. So there's a little bit of a trade-off between what is most efficient in terms of power consumption or cumulative energy consumption and the time to downlink the file. And then we observed that there tends to be an inflection point where we get diminishing returns at frame error rates of about 1 in 10 to the third to 1 in 10 to the fourth. The 2 graphs on the bottom show how CFDP packet size can affect these measurements. So up here, this was for a CFDP PDU size of 1,024 bytes, which is probably smaller than we would realistically go. So here, if we increase packet size, and this graph on the left is transmission time, this dark blue line is the lowest power, highest speed curve. So as we increase CFDP packet size, the time it takes to downlink the file grows pretty rapidly, and that's because the packets are larger, they're more likely to be dropped, and when they are dropped, it's more bits to retransmit. And then there's a similar effect going on here, which shows the cumulative energy consumption. And again, the dark blue is for the low power, high speed, leftmost point on the Ebno curve. So, to bring it all together, the conclusions of the trade study is that network and application layer protocols really don't affect link efficiency substantially. LTP and BP can maintain high link efficiency in lossy environments and reduce the burden on the CNDH processor. However, I think I forgot to mention it in the first phase. There is a little bit of a tension between what's in the interest of, let's say, the flight software team or the mission operations team, and what's in the interest of the telecommunications team. If LTP were to be implemented on the lander, it would probably need to be implemented in the radio. And that produces an extra burden on the telecommunications team to do something that really is out of their scope. But it would be good for the flight software team and the mission operations team, because having these protocols that take care of a lot of the network level issues really reduces the burden, the design complexity on their end. Another major finding is that link layer frame should be as large as possible, and this is the case under all error rates, from whether it's an atrocious error rate or a fantastic error rate. And then finally, better link efficiency doesn't imply lower energy use. And I think that was one of the most important findings that we made here. And that can be rephrased another way, that the cost of retransmissions can be cheaper than the cost of maintaining a perfect channel. So this was really only a portion of the trade study. There's a lot more nuance. There's a lot more architectural diagrams that we could have gone into. So it's been quite condensed for this talk. Most of the participants were in my group at APL, the Embedded Applications group. We also had input from the RF Engineering group, and they work closely with JPL out here. And so that's it. I guess I'll take any questions.
Take the mic. we're looking into using DTN for a couple missions at Goddard.
Mhm.
And one of the other things you need to consider is just the buffer efficiencies. So you have a large data store in CFTP, and now you have a large data store in BP, and then a large data store in LTP, and those really need to be considered.
Okay.
So one of the ways we're working the stack is CFTP into BP, and then aggregate custody direct signaling as a way, so with no LTP in that case. And what we find is that we can actually get the CFTP, as soon as the file is created, deliver it to BP, and do the bulk store there. There is no CFTP bulk store anymore.
And then just free it right away.
Just
in the
freeze it right
CFTP
away,
engine.
and that really, because you can't have 5 gig here and 5 gig here, and then another 5 gig for LTP. So anyway, you need to consider that. I've been working with Ed Brain as well.
Oh, okay.
So I'd like to see some of your more basic data to see and use that spreadsheet. I have the spreadsheet, but I'm not quite sure how to use it.
The one that we used for the first phase that
Ed,
shows the
I
overhead.
think. Yeah.
Okay.
So anyway, I want to follow this up.
Oh, sure. Okay, well, thank you for the comment.